In this video, I am going to solve a problem about statically indeterminate beams using double integration method. Here's the problem. Determine the reactions at the supports A, B, and C, and then draw the shear and moment diagrams. Assume EI is constant. So, okay, this is our beam. So, statically indeterminate because there are 4 unknowns. One unknown for the support at A, since this is a roller support. One also for B, and 2 reaction components at C, since point C is a hinge support. But since there is no horizontal force, therefore the horizontal component of the reaction at C is equal to 0. So there will now be 3 unknown reaction components, one at A, one at B, and then the third one is the vertical component of the reaction at C. So let us start with the equilibrium equations. Now there are 3 equilibrium equations, but then the first equation, which is summation of force along the horizontal, is already satisfied. Okay, since Rx is equal RCX, is equal to 0. So let us now sum up force along the vertical or y-axis. Upward force denoted as positive. So we have RA plus RB plus RC, and then minus 12 minus the resultant of the uniformly distributed load, 3 times 1236. So simplify, transpose the constant terms to the right side, and we have this one. This will be our equation 1. The other equilibrium equation is, or condition, is summation of moment about any point, either A, B, or C. Just pick any of the supports. Okay, suppose let us sum up moment about point C. And we denote counterclockwise movement as positive. So the moment of RA is negative since the direction is clockwise. For RB, negative also since clockwise. For 12, it's positive since the direction is counterclockwise. For this one, positive also. So here's the equation. Negative RA, the distance of RA to point C is 24. RB, the distance is 12. The 12 keep load, the distance is 18. And for the resultant of the uniformly distributed load, 3 times 12, 36. The resultant acts at the centroid. And the distance of the resultant of point C is 1/2 of 12, which is 6. And simplify, we can divide each term by 12. Okay, and the result is this. Okay, this one. 2RA plus RB equal to 36. So multiply and then combine and divide it by 12. The result is 36. This will be our equation number 2. Now, we have 3 unknowns, but we only have 2 equations. So therefore, we need to find an additional equation in order to solve for the reactions. Okay, this is where we're going to use the double integration method. Okay, so using Macaulay bracket function, we will cut a section somewhere sa BC and denote the distance of this cutting section from A as X, and then you have the resisting moment, the internal moment. So we get the equation of moment, or M, we have this one. M equals RA times X. So, originally, if we sum up moment about the cutting section and then we denote counterclockwise as positive, M is counterclockwise positive, RA is negative. But then, all of these terms, we equate it to 0. So, if we transpose everything except M, their signs will be changed. So, RA is negative kay clockwise, no? But when this one is transposed to the other side, it becomes positive. Like this one, no? So, nakatranspose na ni. RA times X. RB, the distance of RB to the cutting section is X minus 12, no? And when we use Macaulay bracket function, instead of parentheses, we replace it by pointed brackets. And the meaning of this is, if the value inside the pointed bracket is negative, then we neglect the term. Negative or 0, we neglect the term. Like when x is 6 or 10 or 9, we neglect this term. So RAX plus RB times x minus 12. This one, 12 is counterclockwise, but when we transpose, it becomes negative. Negative 12, the distance of 12 to the cutting section is x minus 6 now. X and then minus 6, this one. And then for the uniformly distributed, the resultant is 3 times this one. Area of the rectangle, 3 times x minus 12. That's the resultant. 3 times x minus 12. And the distance is, this is where the resultant acts. And the distance of this resultant to the cutting section is 1/2 sa x minus 12, this one. And before we integrate, we simplify this term first. Okay, so after this, we integrate and we have this expression. EI times y prime or dy over dx, integral of this one. Integral of each term. Integral of RAX is RAX squared over 2 and so on. Like 12x minus 6 squared over 2, it becomes 6 times x minus 6 squared. Cube over 3, makancel ang 3. What remains is 1/2 times x minus 12 raised to 3. And then we introduce one constant of integration, C1. And then we integrate further. We have this expression of deflection. EIY equals integral of this equal to this one, and so on. And then we introduce another constant, C sub 2. Okay. So after this, we go to the boundary conditions. Okay. For the boundary conditions, we use the constraints. Like at A, since this is a support, no settlement, therefore the deflection is 0. So our first boundary condition is at x equal to 0, the deflection is equal to 0. At x equal to 0, it means point A. The deflection is equal to 0. So we are going to use this value, substitute this one to the expression of deflection. Okay, y equal to 0. So the left side is equal to 0. X equal to 0. So 0. And then this term will be neglected. Kaya negative man. 0 minus 12 is negative 12. So this term will be neglected or considered as 0. This one neglected also. Negative man. This one neglected also. And x equal to 0. Therefore, our C2 is equal to 0. Okay. The second constraint is this. At point B, since this is a support, the deflection is also equal to 0. and that is x equal to 12. So, at x equal to 12, y equal to 0. Substitute this one against the expression of the deflection. Y equal to 0, x equal to 12, okay. This one, 0, not considered. 12 minus 6, okay. 12 minus 12, 0. And our expression is this, our equation is this. 0 equal to 12 cube over 6. This one will be 0 minus 2. 12 minus 6 is 6 cube. This one, 0, 12 minus 12. And then 12 C1. C2 is 0. So we simplify this one by dividing the equation by 12. Okay, and the result is this. 24 RA plus C1 equals 36. So we transpose the constant term to the other side. This will be equation number 3. And the last constraint is this. At point C, since it is a support, the deflection is 0. And that is when x is equal to 24. So at x equal to 24, y is equal to 0. So 0, 24, okay. 24 minus 12, okay. 24 minus 6, okay. 24 minus 12, okay. And we have this equation. So we simplify this one and then transpose it to the other side. And then we reduce the equation by dividing this by maybe 24. No? Okay. Okay, 24. So, ma-remove ang coefficient sa C1. And this will be our equation 4. Okay. So, with these two additional equations, next step is we eliminate C1. And the resulting equation will be our additional equation in addition to the first two equations, equilibrium equations. Okay, so we will now combine 3 and 4 and then we will eliminate C1. So combine 3 and 4 and then we eliminate C1. So we subtract 3 from 4. So 4 minus 3. And makancel ang C1. 96 minus 24, it's 72 RA. 12 RB. 594 minus 36. It's 558. This will be our fifth equation. So we will now combine this equation to equations 1 and 2 sa equilibrium equations in order to solve for the reactions. So we combine equations 1, 2, and 5. This is equation 1, and then equation 2, and then we add equation number 5. So using your calculator or using method of elimination, you can use equation 2 and 5. You want to eliminate RB, you can solve for RA. Okay, this is RA. And after solving for RA, you can substitute this one to equation 2. This one. Substitute here, you can solve for RB. And to solve for RC, you substitute the values of RA and RB to equation 1. And you can solve for RC. Okay. So the next part of the problem is to draw the shear and moment diagrams. Now remember that when you draw the diagrams, you will only know if your solution is correct if mag-close ang moment diagram. So pag mag-close ang moment diagram, it means na your reactions are correct. Okay. So we will now draw the shear and moment diagrams. This is our beam, and then we supply the values of RA, RB, and RC. So first shear diagram, upward reaction sa A, 2.625, and then from A to the 12 kip load, there is no load. So ang diagram sa shear is horizontal, and then go down by 12. So 2.625 minus 12. The result is negative 9.375. And then from 12 to point B, no load again for this segment. So the diagram is horizontal. And then for B, there is an upward reaction of 30.75. So negative 9.375 plus 30.75. The result is 21.375. And then from this one, we subtract the uniform load. 3 times 12, 36. That's negative, no? So 21.375 minus 36. And we have negative 14.625. Now, remember that from the relation among load, shear, and moment, if the load diagram is a uniformly distributed load, the shear diagram is a straight line. Okay. So, after this, we apply the reaction at C, 14.625 upward. So, mag-close ang shear diagram. Okay. And since we are using the area method of drawing the diagrams, we'll compute for the area of the shear diagram. Now, for this one, we don't have this distance, so i-compute na to x. To solve for x, you can use my technique. This one, shear divided by uniform load. So 21.375 divided by uniform load 3. The result is 7.125. So next is we compute the area. 2.625 times 6. The area is 15.75. Next, negative 9.375 times 6. Negative 56.25. Next, triangle. 1/2 of base times height. This is the area. And this one, area of triangle again. 1/2 of this distance, 12 minus 7.125 times 14.625. The area is this. Okay, so after this, you may now draw the moment diagram. So upward na positive straight line, 15.75. And the next is this one, straight line also. 15.75 minus 56.25. The result is negative 40.5. And then we add this one, 76.1484375. Second degree na. Okay, and the result is this. And then next is we subtract this area, negative 35.6484375. So the result is 0. So this means that our analysis or our solution is correct since nag-close ang moment diagram. Okay, so double integration method, this is where you get the additional equations. No? So if there are two redundant unknowns or simply the problem is indeterminate to the second degree, then we will have two additional equations. Kaya there are four unknowns naman. Okay. Same lang, no? Either you can use method of elimination or Gauss Jordan or determinants, depende sa problem. But mostly, you can do it or you can solve the reactions by just using method of eliminations. So that's it. I hope that you have learned something from this presentation. Thank you for watching.